How do these new animal body plans and fundamentally new forms of life come into existence? This was the mystery that Darwin set out to solve. But everything we've learned in biology over the last 50 years has brought this mystery back with a vengeance. How do you explain the origin of the Cambrian animals seemingly out of nowhere? This isn't just a problem of explaining the absence of evidence in the fossil record. It's also a problem of explaining everything we know about life, right down to the level of molecules and cells.
The biological structure of a Cambrian trilobite was as complex and sophisticated as a modern crab. Its organs included a brain, gut, heart, and compound eyes. Each organ was constructed from specific types of cells. Each cell type was made from dozens of specialized protein molecules. And each protein was assembled from a 4-letter chemical code in a section of DNA called a gene.
Now, for the evolutionary process to transform a simple Precambrian organism like a sponge with 4 or 5 cell types into a Cambrian trilobite with at least 10 times that many different types of cells, that's a huge leap in complexity. And to make that leap, you need a vast amount of new genetic information. Where does that information come from? That's the central mystery of the Cambrian explosion.
According to neo-Darwinism, new proteins are constructed by the dual mechanisms of genetic mutations and natural selection. As the genetic instructions for building proteins are copied, an occasional error can alter their contents. If these accidental revisions prove beneficial to survival, they are selected or preserved and passed on to future generations. Over eons, these small changes accumulate, and new proteins, cell types, and even Cambrian carnivores gradually evolve into existence.
Richard Dawkins, the famous Oxford evolutionary biologist, has illustrated how the Darwinian mechanism works using a metaphor he calls climbing Mount Improbable.
From the front side, the mountain is a sheer cliff that could never be scaled in one giant leap. For Dawkins, this represents the impossibility of creating a complex animal by chance alone. Yet Dawkins also envisioned an alternative route up the backside of Mount Improbable, a long, gradually sloping trail of small steps leading all the way to the summit.
According to Dawkins, that's how you'd climb the mountain. And that's also how you'd build a Cambrian animal, one small step at a time. What chance alone can't accomplish in one blind leap, natural selection can accomplish through the cumulative effect of many small incremental steps.
In theory, each step corresponds to a small unit of biological change, a new gene and its protein product. But do mutations and natural selection have a reasonable chance of producing even one protein in the time available? Since 1992, molecular biologist Doug X has examined this question.
There's a story that's being told, and there's an appeal in the case of Darwinism to random mutation and natural selection as being, in vague terms, the mechanism. But if you look at the detail, what kind of mutation can accomplish these transitions? And there, it's important to realize that the one area where we can really nail this down is at the single protein level, where you can actually measure it. And if you look at protein structures, to get a substantially new protein fold is prohibitively difficult.
Each of the thousands of different proteins in nature is actually a chain made from a specific combination of 20 different amino acids. The sequential order of these chemical building blocks is crucial, for if they are arranged correctly, the chain folds into a functioning three-dimensional molecule. But if the amino acids are incorrectly assembled, no protein will form. If proteins are indeed rare among the possible sequences of amino acids, what are the odds that mutations would stumble upon a functional combination of chemicals from the vast number of alternatives? To find out, X randomly altered the structure of an enzyme protein comprised of 150 amino acids.
You've got the protein 150 amino acids long, then you've got 20 to the 150th power possible ways of arranging the amino acids. Out of all those possibilities, how many are functional and how many are gibberish?
If you do the experiments and you analyze how much information is required to get, say, a new protein fold, it's just far beyond what you can get by random mutation and natural selection.
How far beyond? Axe published his findings in the Journal of Molecular Biology. He determined that among all the possible amino acid combinations, the probability of generating just one short protein by mutation is roughly 1 in 10 to the 74th power, or 1 chance in 100 trillion, 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 trillion.
To put that in context, there's only 10 to the 65 atoms in the entire galaxy. So to build a new functional protein by selection and mutation within the time allowed for the Cambrian explosion, what you're essentially having to do is equivalent to a blindfolded man looking throughout the entire galaxy for one marked atom. So what we're talking about is searching for a tiny, tiny needle in an enormous haystack and having a very limited time to search.
So on the question of something like the Cambrian explosion, there does not appear to be any way that unguided random mutations can accomplish what needs to be accomplished to explain new functional proteins. And certainly by extension, wherever in the history of life you would need to have multiple new protein folds, the probabilities multiply. So there's no reason to think that this is plausible.
But the inability of random mutations to generate new genes and proteins is only part of the problem. For the origin of Cambrian body plans demanded more than new genetic information.
A lot of the information for specifying an Anomalocaris, a trilobite, what have you, it does not reside at the DNA level.
The body plan, as far as we know, is not in the DNA.
While DNA carries the instructions to manufacture proteins, it cannot alone assemble them into cell types or arrange cell types into new tissues and organs, or tissues and organs into body plans. Instead, the formation of body plans ultimately requires another level of information stored somewhere in the three-dimensional structure of the egg cell and the embryo. Instructions that direct the development of complex animals from fertilized eggs. With computer animation, we can observe this intricate process. As an egg cell begins to divide and differentiate, a network of biological commands orchestrates the development of an arthropod. After several stages of division, dozens of new cells align against the outer membrane of the egg. And then, cued by a chemical signal, they start their migration toward targeted areas in the embryo, where they will gather and develop into a mature organism. The cells steadily increase their numbers and align, like members of a marching band, into patterns that will form the tissues and organs, head and legs of the growing embryo.
That happens by a process of cell specification and differentiation, where cells are committed irreversibly to performing particular roles. You're going to give them different jobs to do. You're going to be part of the locomotory system of this organism. You'll be an eye, you'll be a gut, and so forth. To me, that's an absolutely astonishing process, but it works. And what it builds you is different kinds of organisms depending on the instruction set that's provided.